Hello everyone, today I want to talk about a very interesting topic, how language models evolved into fully autonomous agents. As for me, I'm a solution designer, and the reason I wanted to learn about this topic was that I wanted to be able to design better agents. If you have tried to design an agent before, you understand that there are so many ways to reach a certain goal. There are so many prompting techniques, there are so many tool calling framework, and it can get a little bit overwhelming. But what works for me all the time is that when you understand the foundation, and if you understand what's going on under the hood of all this framework, it helps you to design agents that are not only functional but also smart and adaptive as well. So let's begin. To understand the journey of how large language models evolved from just generating tokens from some probability into fully autonomous agents, and to make things much more clearer, I divided the video into 4 key stages. At first stage, I'm going to talk about how LLMs evolved reasoning. We're going to talk about concepts like chain of thought prompting and chain of thought prompting with self-consistency. At the second stage, we're going to talk about how language models learn to actually take actions. We're going to talk about projects like WebGPT, React, and Toolformer. At the third stage, we're going to talk about how language models learn to reflect and learn from their own mistakes and leverage memory and external context to be able to overcome their context size limitations. And at the last but not least part, I'm going to touch a little bit on autonomous agents and talk about a very interesting paper called Voyager, which is a learning agent in Minecraft environment. I hope you enjoy the video. In this part, I'm going to talk about how language models evolve reasoning. And to start, I'm going to give you a very simple example of early days of ChatGPT. So if you work with ChatGPT in early days, if you ask it a very simple mathematical question, sometimes it gives you the correct answer and sometimes the wrong answer. And it was expected because language models at core are just some models that generate the next token based on some probability distribution. So they are estimating the answer. They are not actually calculating the answer. So obviously they struggled with tasks that needs a little bit of reasoning. And hence it brings us to the concept of this section, which is chain of thought prompting. So the core idea of chain of thought prompting is that if a model sees enough examples of reasoning written step by step, it might be able to imitate or copy the same style of reasoning in context and generate better answers. You might already actually use the same concept when you are working with language models. You give examples of how you want the model to do a certain task, and the model follow your instructions and try to generate the answer the same way. So chain of thought prompting is a very simple and powerful concept. But have you ever thought why this works? Why when you give examples in the prompt, the model actually generate better answer? This is to me very interesting, and the core idea here is that because LLMs are autoregressive, it means that they generate one token at a time, and the probability of the next token being generated is very highly dependent of the previous tokens that were generated. Again, just to make you understand a little bit better, I want to give you an analogy. When someone asks you a question, you don't go ahead and just answer in one full paragraph, suddenly out of nowhere. You start talking, and as you talk, you carefully select the next word or next token, and the next word that you choose when you're talking is highly dependent on all the previous words that you have chosen or you have generated. Language models kinda work the same way. So in chain of thought prompting, we are actually forcing the model to generate better intermediate tokens that actually help the model to generate better final answer. So the key idea here is this, and if you want to design an agent that is able to reason better and generate better answer, all you need to do is that force it to generate better intermediate tokens. So as all the good things, this again came with a caveat. So the reasoning only emerge when the size of the model goes above 100 billion parameters. Again, I want to give you an example. If you try to with local LLMs, which are much smaller and you can run them on your own computer, no matter what you do, they cannot do very task that needs a lot of reasoning. And here is why, right? So in their experiment with modeling with different size, they understood that this reasoning only get unlocked if the model size is above 100 billion parameters. Again, a very good takeaway note. So if you want to design an agent and you want it to do reasoning, try to pick a model that the size allow for emergence of the reasoning for your agent. So another concept that is worth talking about, especially here with chain of thought prompting, is self-consistency. And the core idea is how we can statistically improve the accuracy of the results. So I think this diagram helps to understand the idea very well. So on the left, you have your usual path, so your prompt and the output that was generated. In the middle, you see the chain of thought prompting, which you give reasoning step by step, and the model generate the output based on that. And with the chain of thought prompting with self-consistency, so you're giving the same, for example, question to the same model, but you're generating answer, for example, 100 times instead of just one time. By doing so, you are generating 100 different passes of reasoning, which actually can help with increasing the accuracy of the result. You're kind of solving the problem of the estimation statistically. So you are increasing the probability of the answer being correct by sampling more. So if you are answering a mathematical question and your answer out of that 100 times generation, 80 times is 27, the probability that the actual answer is 27 is very high. That's why you're saying, okay, this is the answer. So again, it's come with an issue. So you might say 100 times more generation means a lot of cost. So it might cost a lot of money during inference time. But if you think about how costly it would be to actually train the model again to be able to do this task, meaning the cost for a computation during the training, it might be actually a better or cheaper option to achieve better accuracy. In this part of the video, I'm going to talk about how language models learn to take actions in an environment. And we're going to go through 3 very interesting papers: WebGPT, Toolformer, and React. So to start the section, I'm going to give you again an example. So if you recall very early days of ChatGPT, when you ask it a question about recent events, it would tell you that my training data cutoff period in, for example, 2 years ago, and I cannot answer questions that are related to the events in the last 6 months. So obviously, this showed a huge gap, and it raised the question that do LLMs can actually learn to browse the web and answer the questions and write and cite references like humans do or not? So this is the core idea behind the project WebGPT and how they actually train a model to be able to browse the web. So again, the core idea of the WebGPT was, can we teach LLMs to browse the web and find the answer to the questions like humans do? So again, let's go back of how you actually find answer in the web. So you go to Google or any other search engine, you search for the things that you are looking to find the answer. The search engine will suggest to you some links. You click on each link and scroll up and down in the pages. You might come back, you might click on another link, and once you find your answer, you end the browsing session and kind of answer the question. So in order to force the LLM to imitate that, they created this simulation environment, which at one part you have your agent or language model, and there is an available action space which the language model can select from. So these action space are like the actions that humans take when they are doing browsing. And at one side there are your browser, which was kind of a text-based browser. It was just for simplicity, so all the web pages were translated to text, then fed to LLM. I will go into more details later, but to give you a very high-level idea, as the simulation environment, you have your agent, your simulated browser, web browser, and some available action space that the language model can choose from. So let's go through the WebGPT training pipeline. We wanted to teach the language model to imitate or copy how humans browse the web. So what they did, they hired people to interact with the simulated environment that they created to answer the question. So people were hired, they work with that environment, they take from that action space, the environment would send them some answer, and they captured a lot of full browsing journeys from start to finish that were created by humans in that environment, and they used it as data set to fine-tune the model. So at this step, which was called behavior cloning, the language model kind of learned to copy and imitate how people or humans actually browse the web and answer the question. So far, the behavioral modeling was done. In the next step, we'll talk about reward modeling. So what is that? Again, I want to give you an example that I'm sure you've seen before. So in ChatGPT, sometimes when it's generating answer, it generates two parallel answers and asks you to give feedback which one of them you prefer. Okay, this is the whole purpose of reward modeling block here. So it's trying to understand which answer the user prefer or the human prefer. So the language model learns to generate answers that are more preferable by humans. So this answer might be structured differently, they might have numbering, better conclusion, better start, but it's very costly to hire humans to give you feedback on that model and the answer that the model is generating. Because it's very costly to hire people, another model is trained, which is responsible of estimating which answer actually people prefer. So this is the reward modeling part, which is more on the alignment side. As I mentioned, because we are, for example, users of ChatGPT, it's easier for them now to collect this information from us to be able to better train this model to estimate at large scale which answers are preferred. So be careful which answer you choose because it actually helps the next generations of model and how they generate answers. So far, we talked about a model was trained based on behavioral cloning, then either humans or another model based on human preference, which was reward model, was trained to score those answers, And another trick in the next step comes in handy, which is rejection sampling or best of n trick. So in this trick, you kind of generate n answers. For example, 64, 100, doesn't matter. You pass it on to your reward model for scoring, and whatever answer is scored the highest by your reward model, which kind of shows the human preference, gets selected as the output. So in WebGPT training pipeline, reinforcement learning also was used to be able to improve the browsing policy. The core idea behind reinforcement learning and usage of it here was that to give the model human feedback during the training, not after, during the training, to be able to improve the helpfulness or truthfulness of the answers that was generated. So the concept of reinforcement learning can be a little bit daunting at the start. So I want to give you a very simple example to understand reinforcement learning better. So what is reinforcement learning? So in reinforcement learning, you have an agent that learns a policy based on interaction with an environment, some trial and error, and based on a reward function that it gives a reward to the agent based on the actions that it takes. Okay, to give you an example, consider when a baby is born. They start interacting with their environment, with their parents, and they learn to live based on the feedback or the reward that the parents provide. For example, if they learn to walk or they learn to talk, we reward them and we encourage them and give them positive feedback to be able to repeat that. But if they do something wrong or they break something or do something bad, we give them negative feedback. So that's how they learn to live in the world and interact with the world. That's how they learn a kind of a policy to live in the world. Reinforcement learning works based on the same concept. So you might ask yourself how reinforcement learning will help language model here and to improve the browsing policy. Again, it comes back to the reward or a preference model that human prefer. So to give you another example to understand this better, if you are a student in a school and the exams are designed in a way that you score higher if you memorize the text, as students learn in order to pass the exam, they just need to memorize the text, right? But if the exams questions are designed in a way that it tests the problem solving skills, the students learn that in order to pass the exam, they have to improve their problem solving skills to be able to pass the exam or satisfy that reward model. So you will end up with two different types of a student completely. So the language models are the same. This reward model during the training steer your model towards generating answer in a specific way that humans prefer. But you have to be careful of the reward model that you choose, because it's not just about which one you prefer. You want the answer to actually be correct. You want the LLM to tell the truth to you as well. It's helpful as well. That's why you end up all this product. You have language models with different tones. Some of them are direct, some of them more technical, some of them might be more sweet or helpful. It's just about using reinforcement learning with human feedback to be able to train the model to behave in a certain way. So as you might have guessed, the model performed really well, especially for question and answering setups, the questions that the model couldn't answer previously because of training data limitation. Now it could go and search the web and provide the answer, and also cite the web page that it used to generate the answer as well. So it was very revolutionary and kind of removed one of the limitations of the LLM models that was actually acting and like web browsing. So now consider yourself, if you have an application that is doing a specific task, can you kind of use the same technique to use a language model to be able to work with your application? So you might have an action space that your application allow. All you need to do is you create all these user journeys using these action space. So a lot of them as your training data. Then you can fine tune your model to be able to generate the same journey. And then you just need a reward model to be able to score the result. And then you have a model that can actually act and use your application. So I hope you like this section. Let's go and see how Toolformers and React help the language model further to be able to take actions in the world. So the next paper I want to talk about is React, which combined reasoning and acting in LLMs. And the core idea is let's think out loud while you act. So React has a main loop which consists of 3 parts. The first part is the reasoning or the thought. The next one is the action that LLM takes after thinking. And the third part is the observation or the feedback that the environment gives LLM after it sees the actions. So what is revolutionary about React, which is a very simple but yet powerful concept, is that it's a prompting technique. So again, you don't need expensive fine-tuning or reinforcement learning like WebGPT used to have. So here is everything is completely in prompt, so you don't need to retrain or do anything like that. So obviously it's less expensive. So to give you an example, imagine of how React works. Imagine you're asking the model, what is the hometown of 2021 Nobel Prize winner in physics? So let's see how this React loop works. So the first thought of LLM is, I should want who won the Nobel Prize for physics in 2021. So the action would be searching for the Nobel Prize winner. So once LLM gets the answer from the environment, that would be the observation. So LLM gets some names as observation. So the next thought after LLM has the name would be, I should find this specific person's hometown. So the next action would be searching for the hometown of that specific person, and observation would be actual hometown that the LLM gets as the result of its search query. And at last, just finish and answer the question using these React loop, which is based on thought, action, and observation. So again, what was very interesting about this paper was how they actually designed the experiment and how they tested it in a real environment. So in the next section, I'm going to talk about that. So React was a very interesting prompting technique, but what was more interesting to me is how they designed the experiment and how they actually tested it. So they used something called ALFWorld, which is a text-based household environment, and it was designed to study how AI agents can interact in everyday environments like households. And how it works is that it's completely text-based. So you have a kitchen that is described by some text. There is a table, there is a fridge, there is a sink, and there is an action space that you can do, a list of actions that you can do in this environment. And based on any actions that you take, the state of the environment changes. So you have a new state, which is again described by text. So this was the environment that they used to test how React would kind of result or achieve a task in the environment. So the goal was simple: put a clean apple in the fridge in ALFWorld. And here is a trajectory of the path that LLM took to be able to complete that task. So it first the thought was I need to find an apple, go to the kitchen table. So the observation was in the kitchen table there was an apple. So the thought was apple should be clean, so I need to examine the apple. And the apple, then the observation was the apple is dirty, then I need to clean it, then I need to go to the sink. So now the apple is clean. I have to put the apple now in the fridge. I have to move to the fridge and put the apple in the fridge, and the task is complete. So this was the core idea, which again, as I said, was completely based on prompting and very simple, very powerful, but has its own limitation. So you might have guessed. So this was a simple everyday task. So LLMs might have choose the actions much better. If you have a specific domain, it might be harder or needs more example for the LLM to be able to choose the right action. Also, if the steps to do a task is long, you might exceed the context window of the language model as well. And one of the important limitation is that at any of these steps, if a wrong action or is chosen, the LLM goes through a wrong path and it cannot correct itself. So there is no learning from the mistake or reflection, which led to further studies that we're gonna talk about in the next section of the video, which is about reflection and how language models learn to correct themselves and improve themselves. So this was React, and in the next part I'm gonna talk about Toolformer and how it improved tool calling in language models. In this part, we're gonna talk about Toolformer. And the core idea behind Toolformer is like how to teach LLMs use the right tool to achieve a task. So if you consider how we do tasks without language models or without AI, each task has a specific application that does it. For example, for mathematical calculation, you use a calculator tool. Or for anything regarding the time or calendar, there is a calendar tool. There might be a translation tool that translates to another language. So any application that you can think of, it might have API or something that you can use to achieve a task. So the core idea here is if LLM is asked to do a task, how it can first learn to use the APIs of those tools and how it can actually learn to choose the correct tool for a specific task. So if you, for example, ask a mathematical question, it should use the correct tool, which is a calculator, to answer the question rather than just estimating. So this is the core idea behind Toolformer, and let's see how they train the LLM to be able to achieve so. So they used 5 tools to train the Toolformer, and some of them were like calculator, calendar, translation. So at the first step of training the model, they shown the LLM example of the API usage. So they give you example, for example, how to use the calculator tool or the translation tool or the calendar tool. At the next step, they got a very large text and asked the LLM to, wherever it sees suitable, insert those API calls into the text. So if it sees, for example, something regarding a translation, insert a translation API call. Or if you see mathematics anywhere, insert a calculator API call. So LLM generated, wherever it sees suitable, a lot of candidate API calls. So obviously, not all these API calls are useful, right? So in order to have a proper dataset, a clean dataset for fine-tuning, they removed the API calls that were not contributing to the correct answer. So how they did so, they compared the result with and without tool insertion. So at one part, they had the original text, and the other part, you had a text with the API call inserted by LLM. So at the next step, they executed those API calls. They replaced the result of the API call into the text, and then they compare the result of the answer to see which API call is helping with the more accurate answer. So obviously, because they had the question and answer already. So they removed any unuseful API call from that dataset. Now they have a very clean dataset having the correct calls, useful API calls, and they use that dataset for fine-tuning the model. And what was very interesting about the result is that they used a GPT-J, which is a very small model, and I think is open source and has 6.7 billion parameters. So it is very much more smaller than some of the models that we are using today. But GPT-J, which was fine-tuned based on this new data set, learned to use the tools properly and actually outperform much larger models. So this showed that tool use can actually substitute for sheer scale. So as a result of this training pipeline, the model learned to understand where to use a specific tool, how to use that tool, how to construct the API call and query the tool, and also how to blend the result of the API call back to the generation and continue generating the text. Again, Toolformer was very revolutionary, but I want to emphasize that it needed training and fine-tuning. So if you want to implement the same kind of technique to be able to make LLM work with your own applications or own API, you can follow the same path as well to be able to force a smaller model to interact with your application APIs. So in summary, in this part, we talked about three famous papers. At first, we talked about WebGPT and how fine-tuning and reinforcement learning was used so the language model learned a browsing policy. And then we talked about React and how reasoning and acting was combined so LLM can interact in an everyday environment like ALFWorld, which was a text-based simulation of a household. And the other paper that we talked about was Toolformer, which in there a smaller model was fine-tuned to be able to work with a specific tools that it was trained on, and it was able to know when to use the tool and how to use the tool. And in the next section, we're going to talk about how language models learn from their mistakes and reflect to be able to improve themselves. So in this part, we're going to talk about how language models learn to reflect and learn from their mistakes. So again, I want to give you an example, which I'm sure a lot of you have seen before. If you work with ChatGPT, sometimes when it's coding, it goes to that analyzing mode. And if the code that is generating has error or something, it says, oh, it has this error, I did this wrong, I am regenerating again or fixing it this way. So what it's doing at that moment is that it's reflecting and learning from its own mistake. Because if it doesn't do that, it generates the wrong answer and it wastes a lot of compute or tokens just to generate the wrong answer. But if it self-reflects during doing the task, it can generate better answer. And Reflexion tries to do the same thing. So the core idea in Reflexion is that let's learn from your mistakes. And if you're learning from your past mistakes, obviously there would be a loop in the architecture. So to simplify the architecture, I separated two different modules. based on the paper. So the first part, you have an actor, which think of it like a React agent, which combines reasoning and acting to do a specific task. And what is interesting is that once your React does something, as the next step, it goes to an evaluator. Evaluator looks at the trajectory that the React agent generated, and based on that, decide if the task was a failure or a success. Okay, so if the task was a success, so it's finished. But if the task was failure, it goes to the next module, which is called self-reflection. In the self-reflection module, the failure gets analyzed by LLM, and the input of this module is the task, the trajectory, and the fact that it's now known that this was failed. This module analyzes the full trajectory and give feedback of what might have gone wrong. Okay, then this feedback, which is called self-reflection, gets stored using memory. And your last 2-3 reflection in this achieving the task usually get stored. They notice that the most gains come after 2-3 reflection. Higher than that, the overthinking might hurt, and you will end up in this never-ending loop, and you will not achieve the task. Then this reflection goes back to your React agent, and using this new insight, the React agent tries again, and hopefully in the next or third or fourth try, it's able, using the past reflection, to do that task correctly. So a key takeaway is that if you want your agent to self-reflect, you can add a couple of more modules to give your agent's verbal feedback based on the trajectory of the failure, store it, and then give it in the next trial to your agent so it might be able to solve your task better. This part of the video is very interesting to me because it talks about something that I'm sure all of you encountered when using language model or interacting with AI chatbots, which directly relate to context size of the language models. So if you work with AI chatbot, you might have limitation of the prompt size based on the number of tokens, or even if you do a little bit of chat, after a while, the chatbot might tell you have to start a new chat because you are reaching the limit of the tokens in this chat. So the memory management and how to overcome the context size limitation in LLMs is something that we're going to talk about in this part of the video. And we're going to talk about a very famous paper, MemGPT, which now is renamed to Letta, which is an agent development framework, and how it tackled this problem. Let's look at some of the problems that MemGPT tried to solve. The first one, so if you have, for example, a very long document, a PDF of hundreds of pages of documents, obviously it grows larger than the context size of LLM, so it's hard to for the model to be able to answer questions based on that. So, and another one was about sessions in a chat when you are working with AI chatbot. So you might encounter it yourself when you are talking, for example, with Claude. After a while, it asks you to start a new chat because you're reaching the threshold for the number of tokens for that chat session. Also, if you have multiple separate chats, this separate session, they don't know, they are not aware of each other. So there is no way to actually the model learns or understand what kind of discussion it had before with the user. In current version of ChatGPT, if you enable memory and turn it on, experience that the model remembers or ChatGPT remembers what it talked about with you in your previous sessions, but the early models didn't have this capability. And papers like MemGPT try to solve this problem using different techniques. So let's look at the architecture together. At prompt, the prompt was divided into 3 sections. The first section was about system instructions, so how LLM should work or interact with MemGPT. The next part is about working context. So if I want to give you an analogy, think of working on a context as RAM in an OS, and the external context or recall a storage or archival storage like disk. So information in RAM or in working context are available immediately in language models, so it's very fast, but it's very limited. However, the external storage, which is here the recall storage or the archival storage, acts like a disk, and it's kind of unlimited here. It can be an external database, and it gives the LLM the ability to go behind its context size. And there is another section which is called FIFO queue, which is first in, first out queue, which holds the conversation or most recent messages. You can see a queue manager here, and the main responsibility of queue manager is that it gets triggered once the queue reaches a certain threshold and automatically flush the messages from that FIFO queue to the recall storage. And here is the key point. Once the messages get flushed to the recall storage, still LLM decide what part of those messages should be kept into the working context. So if there is a fact that needs to be kept still in the prompt before moving to the external storage, LLM decides that maybe summarize it or something, put it into the working context, writing into the working context, and then put the old messages into the recall storage. And that's how it empties the queue for more fresh messages. What does archival storage do? So if you have a very long document like a PDF, those kind of messages get stored and written into archival storage, and you have a function executor that is responsible for executing a specific set of functions, for example, writing, searching the recall storage or archival storage, and replacing the text in the working context. So that function executor gets triggered based on a system state and what needs to be happening based on the size of the queue or even the question that the user asks. So if user asks a question that LLM cannot find the answer for it in the working context, it goes and searches the recall storage, or even if it cannot find it, the archival storage to be able to answer user question. So in summary, LLM controls the data movement between the working context, which is inside the prompt, and an external context, which can be a vector DB or a Postgres database. And the data moves in and out of this working context so the user can query the LLM. But as you might have guessed, for this to happen, for the data, for example, to move in and out of the working context, some functions needs to be executed. Maybe the information needs to be summarized and facts get extracted to be able to be put inside the working context. And all of these needs extra LLM calls. So if a heartbeat flag is enabled and is set to true, the language model provides an extra inference session before finalizing everything and answering user query. So you might need multiple LLM calls in order to able answer a certain question. And that's where the heartbeat flag is used. So you don't go back to the user immediately. Once everything is done, then the answer gets generated. So they did multiple experiments to test how the system works and perform. There are a couple of interesting ones that I want to mention. One of them was a deep memory retrieval experiment. So what they did, they initiated multiple chat sessions, separate sessions, and they discussed something with the language model. But five sessions later, they asked a question about what was discussed, for example, in the first session, to see if the LLM remembers what was discussed. And obviously, it performed really well. The second experiment that they did was about conversation openers. So, for example, consider you told the chatbot that you are planning a trip to a certain location. The next time when you are talking with the chatbot or the language models, it start the conversation exactly like a human asking about your trip. It asks the user, how was your trip, for example, because it remembered from the previous chat that you were planning a trip. Another experiment that was done was related to document analysis. So they did task on multi-document question answering. So there are multiple, for example, PDFs that got stored into archival storage, and LLM was able to actually search through all these PDFs page by page to be able to retrieve information. Another interesting thing was that nested key value retrieval or KV retrieval was possible as well. And what is interesting about it is that it kind of unlocked the kind of chain reasoning steps or memory chaining steps. And to kind of open that a little bit, consider the fact that you might search something in a page or something as the key, and it might return a value. However, this value might not be your final answer. This could be the key of your final answer. So LLM start another search based on this value and then get the value of that nested key. So LLM were able to actually do this nested search in document analysis to be able to answer user query as well, which was another success story which wasn't possible for an static prompt before. I hope you like this section. I personally really like this section because, again, it was very powerful because it didn't need training or fine-tuning or coming up a new model to exceed the size of the context size. So the size of the context got limited just by designing and adding external storage and creating a system that decides based on using an LLM what information stay in the prompt and what information go to an external storage. A very famous example of usage of this kind of design or techniques is in ChatGPT itself. If you enable memory, ChatGPT will remember, for example, your name, the conversation you had with it. Even there was a very famous trend going on that people would ask ChatGPT to generate a picture based on their character or personality and what it knows from them so far. And it all works kind of based on the same concept. It kind of store what it finds interesting or important about you. For example, if you tell the model about your job, about your children name, your spouse name, LLM decide this information is worthy to keep it in the somewhere in the either the prompt or an external storage and retrieve it when needed to have more meaningful conversation with the user or answer user questions better. So in this part of the video, which is the last part, I'm going to touch on a little bit on autonomous agent, and the paper I'm going to talk about is called Voyager. So Voyager is an agent that its task or objective is to build skills. So the objective is not to achieve a certain task or goal, but the main goal is to build a library of skill sets where very interestingly in Minecraft environment. So if you have worked or played with Minecraft environment before, you might have guessed why this is a perfect setup for an AI agent to build a skill set. So in Minecraft, there is no condition of win. So the AI agent can explore indefinitely and build skills, learn things in a very creative manner. And also the progression of the agent is easily consumable by human watching this experiment as well. So that's why Minecraft was selected. So the Voyager architecture consists of three main parts that work closely together to build this library of skills. The first part is automatic curriculum, which the objective of this part is to define goals for the agents to achieve certain things. How these goals are defined? These goals are defined based on a state of the agent and the environment, the inventory, and the skill sets or the library of a skill that the agent already have. So once the task is set by the automatic curriculum, which is an AI, it can be, for example, ChatGPT. Once the task is set or objective is set, it goes to the next part, which is iterative prompting mechanism. On that part, code gets generated to do that specific task in Minecraft environment. Then that bit of code that was generated to that specific task gets executed in Minecraft environment. If the task was achieved successfully, it gets added as a new skill to the third part of the architecture, which is a skill library. So you can have the skill as the key and the value in that storage as the code that was executed in the environment to achieve that specific task. So once that task is complete and the code is stored as a skill in the library, the environment state gets updated and gets feedback to the automatic curriculum to set up a new goal. However, if the code that was generated was not successful, it goes back to refine the program. So the codes get generated again and it gets executed again in the environment to see that if this time in this trial the task was achieved or not. So who decides that? There is a self-verification module that decides if the code execution was successful or not, and if this needs to go for further generation of the code, or it can get stored as a skill set in the skill library. Again, very a simple but powerful idea which created an agent that is able to develop and store a skill set a long time, and it can reuse the skill set that are in a skill library. So if LLM or the agent wants to do the task again in another setup or in another condition, it can go to that skill library, search for the key, retrieve the code and execute that code again to be able to achieve a certain task. The performance of Voyager was kind of measured by different metrics. Some of the metrics were the exploration distance, the number of skills that were acquired, the state progression, the total number of items in the inventory, and they were kind of compared with different types of agents, which some of them were mentioned in this video. For example, Reflexion, React, and it was observed that Voyager outperformed all of those agents because of the fact that it was able to combine all of these previous methods together. It was able to do reasoning to come up with better goals. It was able to act and execute code in the environment. It was able to reflect and correct the wrong code that was generated, and it was also able to store the skills that it acquired and retrieve them later for another task. So it kind of combined all of the concepts that we discussed today in this video, and that's why it kind of outperformed a lot of other types of agents. I hope you enjoyed the video. I put the link of all the papers that I walked you through below, but please go through the papers yourself and read them yourself. The whole video was kind of my own understanding of the topic, but I'm not an AI expert, so please do your own research. And I hope you enjoyed the video. Thanks.